I'm not dedicating time on parameter estimation for distribution. Let's assume that there is a way to compute these parameters, which is very simple, by the way, but I don't want now to spend time on that. Let's assume then that we have the parameters of the Gaussian distribution, and let's say that we have, for instance, the Gaussian distribution. Usually it's indicated with the symbol n, which stands for normal. And let's suppose that we have a Gaussian distribution 0, 1, which means mean 0 and standard deviation 1. By the way, this is also called the canonical Gaussian distribution. When you have mean 0 and the standard deviation 1, you are dealing with a canonical Gaussian distribution. Okay, so let's suppose that we have this distribution. We have two ways basically for performing simulation. First of all, the simplest way is to start R and write on R this instruction. I'm writing capital letters to make it more understandable, but with R you have to use lowercase letters. R norm 1, for instance, 1000, where 1000 is the number of outcomes that you want. If you digit in R, if you type in R this instruction, R gives back to you 1000 numbers that are sampled. Sampled means taken, extracted from the normal distribution with parameters 0 and 1. If you want different parameters, you have just to change. This is equivalent to the instruction that I gave before. The instruction rnorm wants as three first parameters the number of outcomes, the mean of the distribution, and the standard deviation. So this is very simple if you do it in R, and you can change the parameters. You can also call the help of rnorm, and you get everything. I just would like to mention that with the instruction qnorm x01, you get in this case the probability density of a given value lowercase x for given by the Gaussian distribution with mean 0 and standard deviation 1. I don't remember if qnorm is density or probability of not exceedance. You should check on the help. I don't remember now. I think it's probability of not exceedance indeed, but you should check. Or you should make an attempt just by trying for increasing value of x, and you see if the qnorm increases or after a while decreases. Because I remember to you that probability density is like so. The cumulative probability is like so. Therefore, the cumulative always increases while the density after the mean decreases. So it's very easy to check if it gives to you the density or the cumulative probability. But indeed, if I make reference to a software, it's not a good way to teach how to compute, how to generate synthetic data. So let me now try to explain how rigorously we should do to generate data from the Gaussian distribution. It's very easy indeed. Because first of all, you have two steps. First of all, let's suppose that you want 1000 outcomes. First of all, you should generate 1000 outcomes from what? From the uniform 0-1 distribution. Now you can understand why I introduced the uniform distribution. This is the first step. You need to generate 1000 outcomes from the uniform 0-1 distribution. And to compute the relationship x equal to the inverse of the Gaussian distribution applied to the uniform 0, 1. So let me to better explain. What I generated with the uniform distribution, number comprised between 0 and 1, are probabilities. Probabilities of not exceedance. And then, from these probabilities, I compute the inverse of the cumulative normal distribution to get the Gaussian values. This is because if you want to generate outcomes from a probability distributions, you first have to simulate the probabilities and then computing the inverse of the distribution. The probabilities can occur randomly between 0 and 1 with uniform distribution, because if you just, let's suppose that you have a box with 10 numbers inside from 1 to 10. If you just put an end in the box and you pick up 1, you have a uniform probability of getting every number in the box, because you put the end in the box and you get like 1 or 7 or 6. The probability is uniform because you have 10 pieces of papers with numbers. So if you put an end, you have uniform probability of getting every number. But if the numbers are uniformly distributed, that's it, like from 1 to 10. But you may have, for instance, 10 pieces of papers where you have not uniformly distributed numbers. You may start from 1 and then jump to 5 and have 5 numbers 5, and then 1, 6, 1, 7, and then 3, 8, for instance. It means that you have inside the box a uniform probability of getting any piece of paper, but numbers on the paper follow a different distribution than uniform, because if you put on the paper from 1 to 10, or let's say from 1 to 5, you see you have 5 pieces of papers, and the random variables are uniformly distributed over the piece of paper. But if you have like 2, 3, 3, 3, and 4, this is not a uniform distribution, this is different. This is a distribution that concentrates more probability in the middle and less probability in the tails. And therefore, you have a uniform distribution of getting the piece of paper, but the number on the paper are not uniform. So in this case, you have a uniform distribution here, getting probabilities, and then you compute the inverse of the Gaussian to fully respect the distribution of the random variable, which is Gaussian. Okay, this is a theoretical procedure, and it can be done with the software. What is important to note for our purposes is that this is a procedure to simulate outcome from a distribution, probability distribution. But, as I said before, we cannot simulate river flows in this way. Even if I computed the probability distribution of the river flows for the Po River, I cannot use this procedure for simulating the river flow of the Po River. Why? Be careful, why? Let's note that when I generate synthetic data in a statistical way, but also in any way, we want to reproduce the statistical properties of the process, of the observed data. We want, again, to reproduce the statistical properties of the observed data. In general, we want to reproduce the behaviors of the observed data. And the statistical properties are a subset of the overall behaviors. So I have a river flow process. I have the Po River delivering flows. If I generate synthetic data, I want to reproduce exactly what's occurring in the reality. it means that I have to well reproduce the behaviors of the process. It means that among the behaviors, I have to well reproduce the statistical properties. I think this is quite obvious, intuitive. Well, if I use this procedure, I am making sure that observed and simulated data have the same probability distribution. But there is something more. There is the memory properties, which means the fact that when I have an high flow, the next day I am expecting an high flow as well. These memory properties are statistical properties. They are not taken into account by the probability distribution. So if you make sure that you reproduce well the probability distribution, you are not sure to reproduce the memory properties, if any. So if you have memory in the process, by using this procedure, by making sure that you reproduce the probability distribution, you are not sure that you are getting the memory. I would say you are sure not to get the memory. And let me give you another example. Take the river flow of the Po River and compute the probability distribution. Fine, this is easy to do, as I explained. Now, let's shuffle the data, which means, like un mazzo di carte, you mix them. If you mix the data, you shuffle the data, I'm sorry that I can't show you on the PC, you destroy the memory properties, because of course, you put, if you shuffle the data, you put the observation of the 1st of January, soon after the observation of the 30th of April, you destroy the calendar sequence, and therefore you destroy the memory properties, but the probability distribution doesn't change, because you have still the same numbers. Same numbers. So when you compute the frequency of each number, it's unchanged. It doesn't matter if it is placed on the 1st of January or the 31st of December. It doesn't matter. So you understand that this probability distribution, which remains the same even if you shuffle the data, cannot reproduce the memory properties of the system. So the simulation procedure is good, is correct to use if you don't have any memory in your data. But if you have memory, then you can't use it. So you have to use another solution, and the solution to be used is the stochastic processes. I already introduced to you the difference between a random variable and a stochastic process. Now let me be more clear, because the stochastic process, in addition to the random variable, has the nice feature of preserving the probability distribution plus the memory properties. So this is what interests us. What is a stochastic process? It is a nasty word, but just keep in mind that stochastic is a synonymous for random. So with probability distribution, we dealt with a random variable. In this case, we turn to a random process. The word variable is substituted by the word process, which means that you are considering a sequence, a process. A process intuitively is a sequence of data, not just one number. So stochastic process, what is a stochastic process? The definition is very simple, but I don't understand why still students don't remember it. So this is a classical question for the examination. What is a stochastic process? And I ask this question because it's simple, as you will see the definition from the definition, but still, the stochastic process is a family of random variables. It's a family of random variables. So it's not just one, but it's many. And what's the reason why I consider many of them? because I have to reproduce the memory. So to reproduce the memory, when I generate, for instance, a random variable, I can't generate that variable alone. I have to generate a sequence if I want to keep the memory. So this is the reason why I have to turn to a family of random variables. And you can understand that the simulation procedure becomes a bit more complicated because it's not just a number that you have to create. You have to create, to generate a sequence of numbers. It's not much complicated as you will see, but of course it's a bit more complicated. First of all, you can easily understand that to build a stochastic process, you need to decipher the memory structure of your natural process. So we have to infer the memory of the natural process. Infer means to understand, to quantitatively define. Infer is a term that is used in statistics, to infer. In Italian is inferire. It is used in statistics, means that you understand from a statistical point of view. So we have to infer the memory of the process, first of all. Like for random variables, we have to infer the probability distribution. In this case, in the case of the processes, besides the distribution, I have to infer the memory. So I need one more analysis tool, which is very simple indeed, but we have to define it. And the tool is the correlation coefficient. The tool is the correlation coefficient. Let me see if I am forgetting something. I would say not. What is the correlation coefficient? It's an index that measures the memory of a process, and it's defined depending on the leg of the memory. The leg is a ritardo in Italian. Of course, if you want to quantify how much the polymer remembers of its past, you can understand intuitively that if the past is yesterday, the memory is still very, very, very strong. But if you go much farther in the past, then the memory goes down, of course. So when you want to quantify the memory, you have also to specify what is the legs, how much you go into the past. So this coefficient, which is usually indicated with the symbol rho, is expressed depending on the leg. So you will often find the symbol rho of L. And the correlation coefficient, I give to you the relationship to estimate it from a sequence of numbers, not its definition, because the definition is complicated. What we need in practice is to know the way to estimate it from a series of numbers. So I'm giving to you this relationship. And the relationship is given by the summation. Let's suppose that you have capital N numbers. So the summation is extended from I equal to 1 to capital N minus L of summation of, let me write down, of, at the numerator you have xi minus μx, which multiplies xi minus L. I change a bit the extremes of the summation. I put the 1 minus L, 1 plus L here, and N as extreme limit minus Mx. So at the numerator you have a multiplication between two terms. The first is xi minus the mean, the average value. The second is xi minus L minus the mean. At the denominator you have sigma square x, which is standard deviation squared. And here you divide by n minus L. So, it can be proved. Did I introduce already to you the correlation coefficient last time? Because 2 weeks passed and I don't remember. Okay, fine. It can be proved that minus 1 is the lower limit for rho L of x, and the upper limit is 1. This can be proved. We don't prove it. And let's try to understand physically one fact, that if you have rho tending to 1, you have a strong memory of the system. The system keeps memory of the past, and let's understand this statement. Let's look at the numerator. And what is the numerator? As I said, it's the multiplication between two terms which are given by the differences with respect to the mean of the random variable. So let me try to draw a graph. Let's suppose that I want to draw a graph of xt, which is our random variable with respect to t. And let's suppose that the mean value is here. And let's suppose that the random variable has no memory. What would you expect? You would expect something like this. So if the random variable has no memory, it goes around the mean randomly. If it has memory, what you expect is something like this. Like river flows, you get a high flow period, which is followed by a drought period, and then another high flow period. And this is quite understandable, because memory, what does it mean, memory? It means that if you get to an high level, you keep this high level for a while. The opposite for the low level, you keep it for a while. And this means memory. Indeed, memory means cycles. So, if you have a cycle, you see that if you multiply the variable minus the mean, which is positive if you are in a high cycle, you multiply this variable, this value, which is higher than the mean, for the previous one, you are expecting that the previous one is also higher than the mean. So the product is positive. When you get in a drought period, you have two negatives. Product is again positive. So you understand that you have a high chance of getting a positive numerator. So if you accept that the upper limit of this coefficient is 1, you should try to compute it, and you will see that you don't get values upper than 1. It can be proved, as I said. Let's accept it. Then you understand that for increasing memory, you are getting close to the upper level. So we have proved that for a strong memory of the system, we should get 1 here, close to 1. Instead, if you don't have memory, you have a high chance of getting the product here of a positive value with a negative value with the same likelihood then to negative or to positive. So it means that sometimes you get a positive numerator, sometimes you get a negative numerator, and you get close to zero because they compensate each other. And what happens when you get this situation? Let me draw an our case here. Let's suppose that regularly you have, let's suppose that this is the mean. Let's suppose that regularly you have a thing like this. Then you get always the product of a positive with a negative with a positive with a negative. So you tend to get always negative numerators, which means that you get a negative value of the correlation coefficient. And therefore, you can understand that in this case you approach -1. So you have three different situations. One is negative correlation. Negative correlation is present in a time series where, with the regularity, you have positive values that are followed by negative ones and so forth. Where with positive and negative, I mean higher than the mean or lower than the mean. So if you have this situation occurring regularly, positive, negative, you get negative correlation. If you have a situation which is random, then you get zero, no correlation. If you get a situation with cycles, you have positive correlation. So this index, rho x, depending on the delay, on the lag, L, gives to you important information about the process. And this coefficient is defined for a given L. But of course you can draw a graph which is called the autocorrelation function, where you depict rho x L depending on L for any value of L. L is integer, and for any value, negative or positive, you can compute it. And what we are expecting from here? First of all, let's look at what happens for L equal to 0. For L equal to 0, you get here xi minus the mean times xi again minus the mean. So you get xi square, xi minus the mean square, which is what? If you sum xi minus the mean square, you get nothing else than the standard deviation of the series. If you divide the sum by 1 minus over n, you get the standard deviation. So you get standard deviation here, and it means that the correlation coefficient is 1. Which is of course obvious, because 1 means the maximum of the memory. And of course, if you compare a variable with itself, you get the maximum of the memory. Okay, so here we pass from 1. And for increasing L, what we expect, let's concentrate on hydrology. Therefore, we expect a positive correlation, which tends to 0 for increasing delay, for increasing lag. So this is what we expect in hydrology. The higher this function is, the strongest the memory is. And what about the negative values of L, very easy, it's symmetric. Look at this relationship here, and you will see that it's symmetric. For negative L's, you get the same result than for positive L's. The only thing, okay, it's okay. Let me think about, no, the only thing is that you have to adapt here the extremes of the summation. If you get negative L's, you have to adapt the extreme of the summation, because you can't go back before then I equal to 1. So you have to adapt this extreme of the summation, and also you have to adapt this term here, because you have always to divide by n minus L, n minus absolute value of L in this case. So you have to adapt this the notation, but if you focus on the formula, you will see that it's symmetric. So this is what we expect. And this is the autocorrelation function. And let me now be more precise about the terminology. Here I spoke about correlation coefficient, and now I use the term autocorrelation. What's the difference between correlation and autocorrelation? And please note that very often autocorrelation is just called correlation. But if you use the prefix auto, it means that you are computing the correlation of a variable on itself, on its past. So in the case of river flows for the Po River, you are computing the correlation of the flows of the Po River with respect to past flows of the Po River, as this formula says. So in this case, it's correct to use the prefix auto, but this definition is very general. It could be used to compute the correlation between the flows of the Po River against the flows of the Danube River. Well, one may want to know if they are correlated. So you could use here two different variables. This one could be also a yi. No problem in doing so. There is some difference, because for instance, at like 0 you don't get 1 anymore, not necessarily, but you get an indication of the memory of two systems for leg equal to 0. And also the correlation is no more symmetric. The function is no more symmetric. Because you see here, if you change the sign now of L, it changes. This relationship is no more symmetric. So there are some differences, but you can compute the memory between two different processes, and in this case you can't use the prefix auto. You should use the prefix cross correlation. This function that I introduced, cross correlation or autocorrelation, is very much useful to understand a system. So if you get a series of data and you show me the autocorrelation function, I can tell you, and I knew that it's an hydrological variable, I could tell you whether it's rainfall, whether it's river flow, and if it's river flow, if it's a huge river or not, or other things. So it's an information that is very much useful. This function tells you how much the system remembers its past, or how much the system is dependent on another system. So it's really a powerful tool. And for this reason, usually when I get a time series to analyze, the first thing that I look at is the plot of the time series, because if you look at numbers, this is very much important. To look at numbers is the way of getting the major part of the information. But then, usually, before the probability distribution, I look at the autocorrelation function, because it's really something that tells us much information. And again, what is the autocorrelation function? What is the correlation function? Is a way to decipher the memory of the system. And we need to decipher the memory of the system because we want to generate series that have the same behaviors that observed ones. Okay, now the next step is how to reproduce this. Because we already know how to reproduce the probability distribution for data that are not dependent. Now the next question is how to reproduce then the memory properties besides then the probability distribution. To do so, of course, we need a stochastic process. And there are many possible stochastic processes. In the same way as we have many possible probability distributions, in the same way we have many options for stochastic processes. And what is the difference, you remember, between probability distribution is the shape of the distribution of the density, of the probability density. So the Gaussian has a bell shape, the uniform is given by a horizontal line, and stochastic processes differs not only for their probability distribution, because any stochastic process is characterized by a probability distribution, but the difference is not only the probability distribution, but also the shape of the resulting autocorrelation. So the stochastic process is characterized by its own probability distribution and its own autocorrelation. And there are many of them, and we will consider linear processes, meaning that the relationship